Hello everyone, this is Mohammad Abdulaziz and this is the second tutorial for the Function Data Structures course. Today I'll be again doing some exercises. And they're all in the sheet, and you'll find them in the same repository as last time. But before I start with the exercises, I would like to just tell you that if you have any background, if you have any comments on these tutorials, or if you think of ways to improve them, please post them on Piazza or write them in the comments section on the YouTube channel. So I will start now with the tutorial. So in the first problem, you're asked basically to understand the fold function. Okay, so the first thing I will just show you what the fold function is. So in Isabelle we have a left fold function, and you can see it, for example, by writing that down. So a fold function of the empty list. Okay, so let me just go to the definition of the actual fold function. So that is the definition of the fold function. So fold function. Fold function takes a function that maps types alpha two arguments of type. The first one of type alpha and the second one of type beta to a result of type beta, and it takes a list of elements of type alpha and a third argument, which is an accumulator of type beta, and the whole thing returns an element of type beta. Okay. So so this function is defined as a primitive recursive function, as in the recursive definition of the function follows the data type of the list it follows the structure of an algebraic data type that is defined, and here in this case it's the list. So the recursion schema is just exactly corresponds to the way lists are constructed. So you have a case for empty lists and a case for a list with an element cons to its head or appended to its head. Okay. So in the case when we have an empty list, so the function here returns an ID function, and what that means, so the full function here is defined in a way such that it actually returns a function that takes the accumulator and returns to the beta. Okay, so if you have an empty if you're given an empty list, the full function returns to you just the ID function, which basically means you will get when you apply this fold to the accumulator, to an accumulator, you get the same value of that accumulator because the list was empty. But on the other hand, if you give it a list with an element x at its head, what it returns to you is a composition of those two functions. So this function here, f of x. So this is the one that will take the accumulator that you given as an argument, and then whatever it returns will be used as the accumulator for that recursive call. Okay, so basically you call the fold function on the remaining list x's, and you give as an accumulator to that recursive call the function f of x and the accumulator that is to be given as an argument. Okay. So here in this question, you're required to define a function that adds all the elements in the list, and you're required to do it in two ways. The first one is a recursive way, which should be a primitive recursive way, and the second way should be done with a fold function. Okay. So you should probably pause the video for a few minutes and try to define the recursive one first, but I will continue defining it now. So it should be fun list sum so it takes a list of natural numbers and it gives you a natural number, okay, and it will be just to be recursive on the list, in the given list. So list sum of the NP should equal 0, and the second case is list sum of x and x's, and that should give us x plus list sum. Okay, so I hope that is clear. So just to try and see whether it returns what we're expecting. So I will just do list sum of say 1, 2, and 3. Okay, and here we don't even need to tell it that the types of these are nats, because the types are fixed from the definition of the function list sum, so it gives you 6. So it returns what we expect. Okay, so now we want to define a new function, a new sum function that's based on fold. Okay, so let's look again at fold. So we basically want to fold the list and return its sum. Okay, so that shouldn't be a recursive function, that and it should be just defined using definition, because it's not a recursive function. It is more, it's rather an abbreviation of some expression that will be written in terms of fold. Okay, so list sum prime, which is the other one, it also takes a nat list and returns a nat. So yeah, you should pause it and try and write it yourself, but I will write it now. So this sum prime, many list x's should be equal. So the way I wrote that equal is, by the way, is just writing two equals, and then it suggests to me the equivalent definition. And just also as a tip for you to make these suggestions come quickly, so you should go to plugins, plugin options, and there is an area for delays, completion delay, yeah, and you should put that into 0 instead of half a second, so that you get these suggestions quicker. Okay. So anyway, so this sum of x's equals fold of the addition function and x's and 0. Okay. So what that, so let's try it again. So it's the same result. So now what we need to prove is that both functions are equal. Okay. So before I go to that, I just would like to linger a little bit here and tell you, try and explain that definition. So basically here you're given the function. So as I showed you earlier, fold takes as a first argument is a function, and here in this case it is the plus function. Okay, so that function takes two arguments. The first one is of type alpha, which is the type of the elements of the list, and the second one is of type beta, which is the type of the accumulator. Okay, So here we have the accumulator is a 0, so it's a natural number. I'll just write it more explicitly. That's the accumulator, and the list x's is of type nat list, okay? And because it comes from that type constraint, okay? So that's the plus, okay? So and the list that we get for the fold is just the list x's, and the accumulator, which is basically the initial value, is 0, okay? And then the when you call the fold function, it will start by the first element plus 0, and then the return of that will be added to the second element of the list, etc. So we need to prove that both functions are equivalent now. So let us do that. So the lemma should say list sum x's equals list sum of x's sum prime of x. Okay. Okay. So here we have that thing. We have that statement, and the default way to try and prove it is to prove it by induction on the list x's, and to try and apply O2 and see what happens. Okay, so firstly, we want to show that list sum on the empty list is a zero. Okay, so the list sum of prime of empty list is 0. So the way we do we do that is by giving O2 as a simplification rule the definition of list sum prime. Okay, and the reason we do that is that list sum prime is a definition, not a recursive function. So by default, it's not unfolded. You have to explicitly tell O2 or sim that you need to use the definition as an unfolding rule. So here we unfold that definition by giving it to O2 as a simplification rule. Okay, and let me just show you how that definition looks like also. So the definition is just a theorem, an equality that looks like that, which is exactly equivalent to that, and then when you give it to O2 like that, it will rewrite as usual from left to right. So it will rewrite any occurrence of that, any occurrence that matches that will be rewritten into that, and x's will be substituted properly. Okay, so when we do that, we discharge the first goal, and the second goal is transformed into that. Okay, so here we have this induction hypothesis, and okay, so the induction hypothesis seems like it was applied already. So this one must have been unfolded into A plus list sum of x's, and from the induction hypothesis we know that list sum of x's equals list sum prime of x's. So that was applied when we just said the O2, and then we have the result. So A plus list sum prime of x's, which was unfolded to that by this rule, is equal to the fold plus x's given with A given as an initial accumulator. Okay, so that obviously doesn't follow from the induction hypothesis here, and the way I would approach that is by proving a separate lemma that basically says exactly that thing. So, or actually no, well maybe we can do something else. So we will do a lemma that says fold plus x's. Yeah, we can change the whole theorem statement where we can just start by proving something else. So we can just prove that might work better. So we can just say fold plus x is A equals list sum of x's plus a. Okay, so why is that? Why do we need to do that? It is because when we started proving this lemma directed by induction, what we had as an induction hypothesis had the constant 0 fixed in it in the hypothesis. Okay, and well, what we want the hypothesis also to apply to we want a more general induction hypothesis that applies to accumulators other than 0. And the way you can do that is by actually unfolding this sum prime and write it in a lemma like that and making it explicitly start with an accumulator that's not 0. And here you would modify the other side appropriately. So let's just switch those so that the equivalency between the two lemmas can be clear. Okay. So here that's that, but with the initial accumulator, and that is that also with the initial accumulator. Okay, arbitrary addition accumulator. Okay, so let's try and prove that by induction. So we don't need that definition anymore. So now we have list sum x's plus a and fold and that expression. Okay, that's another hypothesis, and here we have that and that. Okay. Yeah, so we need, okay, so I will switch this again, sorry. Because, okay, I'll tell you why I switched this again. Because I basically want the simplifier to immediately be able to use the induction hypothesis to substitute that into something that, into basically that, okay? And in order for me to enable the simplifier to do that, I will switch the theorem statement, okay? So that because the simplifier writes from left to right, okay? So now, yeah, so, okay, so it, yeah, yeah, okay, it didn't work again. And the reason for that is because, okay, as I was saying, we want to write from left to right, so we want basically something that matches that to be written into that, okay? But nothing matches that because the actual goal that we have has an extra AA in it, so it starts with an initial accumulator of AA plus A, okay? And the way for you to get the induction hypothesis to apply to that is actually by generalizing the statement. Instead of having the statement proven for just this specific A, we need to basically quantify over all A's, okay? So one way to do that is to just say this, and this way we have a general induction hypothesis. Instead of having, so you see here the extra quantifier here, so this induction hypothesis applies to any possible A. So, so this induction hypothesis applies to any possible A, and that will, in our case, be this A plus double A. Okay, so let's see, yeah, so the goal is gone. Another way to do that quantification, which is actually a better way in my opinion, is just to say arbitrary A. So basically this generalizes your induction hypothesis to be for arbitrary A's. Okay, so in this case we have the proof like that. Okay, so now we have this lemma. Auxiliary lemma, okay, and now we can show that theorem by just using that auxiliary lemma by basically unfolding the definition of list sum prime def, and then rewriting that term for that right hand side using this lemma. This auxiliary lemma. Okay, so we do this, and then the goal is gone. So basically, what I'm doing here is I'm trying to get that to be rewritten to list some x's plus 0 by using this lemma, because if you give O2 as a simp argument a lemma, it has to be an equality, and it will be used in a way such that the left hand side is always substituted with the right hand side. So that's what I did here, and that finalizes that proof. Okay, so now let us start with the second exercise. So what is required here is to basically define some form of binary trees, and then define a function that does folding but on those binary trees. Okay. So let's just focus on defining binary tree and how to define it in Isabelle. Okay. So we use the data type package to define algebraic data types like binary trees or lists or other data types that could be basically defined in a recursive fashion. Okay, and I will just in this section, in this question, we need to define the type for a tree, and this should be a binary tree that stores data only at leaves. Okay, so you should pause for a few minutes and then play again, but I will do it now. So data type alpha tree. So it should have two constructors, either a leaf, okay, and that leaf should contain data of type alpha, or it should be a node, and that node should have a left subtree of type L3 also, or a right subtree of type L3. Okay, but it doesn't have any data. Okay, if for example if we want to modify this data type to contain data also in the inner nodes, we would do that. So in this case, we have the left subtree and data of type alpha, and the right subtree of type alpha tree. But in this case, so a node, an inner node, only has two components. The first one is a tree, is an alpha tree, and the second one is an alpha tree, but it doesn't have any data in itself. Okay. So now let us define a function that traverses the elements of these trees in order. Okay, so that should be a definition that is recursive on the input tree. Okay, so it should probably be just primitive recursive, as in it should exactly follow this pattern here. So it should pattern match with a leaf or with an inner node, and act accordingly, act appropriately in either one, in either case. Okay. So that function should be that. So we should be taking an alpha L3 and returning just a normal list. Okay. Signature. So you should pause this video, but I will write it here now. You should pause and write yourself. So in order of a leaf that has data content X should only be a singleton list. Okay. And here it's giving us a warning because we still didn't finish the other patterns, which is mainly the pattern of the inner node. So that's when I'll be doing that. So here we have in order of node L R. Okay, so that node has a left tree and a right tree, L and R. Okay, and in this case, what you should be doing is recursively calling yourself on the left tree and then appending the result to the recursive call on the right subtree. Okay, so let's try and see whether that function gives us what we want. So let me actually show you how to write a term of type tree. So a tree, for example, if I want to represent this tree here that I will show immediately, to represent that tree instead. So a tree like this, and then it has 1 here and 2 there, and then 3 there. Okay, and those are the leaves here. Okay. So in this case, what we would do is to say node, okay, and then this is basically the root node there, okay, and then what is the left sub? We have a left subtree, okay, and that left subtree is also will have a node. It's not a leaf, okay. So in order for us to specify that, so we're going to write node again, and then that node has a left and a right subtrees, and each of them are the leaves, either 1 or 2 here. Okay, so node leaf 1 and the other leaf 2. Okay, and the right subtree of that node there, which is equivalent to that here, is going to be a leaf 3. Okay, so that is how we would specify this tree that we have there in Isabelle. Okay, so let us now try our function in order on that tree, and the way we do it is again by using value. So firstly we have value, we need to make this into, we need to give it a type instead of just having arbitrary constants, because if you don't tell it that those are natural numbers, it will treat them as arbitrary constants. So that's the tree. Okay, and then I want the value of in order of that tree. So as you can see, it's 1, 2, 3, and it follows it does it correctly. And so the next thing that we need to do here is so after defining that in order function, we need to define a function that folds over trees. Okay, and that function should basically be equivalent to applying the left fold that I showed, that we talked about in the first exercise, but applying that to the in order traversal list of the given tree. Okay, so we can just use we can just use that function. So fold f order s. Okay, so we can just, for any given tree, we can just, and a function and an initial accumulator, we can just use that. But I want us to define it in a way that is recursive on the given tree. And again, I think we will not need anything more than just primitive recursion on the given tree. So what we want to define here is a function fold tree, for example. What are we calling it in the sheets? Fold L3, yeah. So that is the initial function, okay? That's the function f that is supposed to take elements of the type alpha, which are the elements of the tree, and an element of type s, which is the accumulator, and return a final element that is of the type accumulator. Okay, so then alpha, another L3, and then here an s, and the accumulator, and then the result. Okay, so we want to define that function recursively over the tree. Okay, so let me just show you what that function should be doing, and then based on that, we can write the recursive definition with each other. But I would like you firstly to try it by yourself. Okay, and then play. Suppose, try it, and then play. Okay. So what we want is a function that, given an initial accumulator, for example, in this case, if we take an accumulator 0 and we want to fold plus on the tree and 0, we want the function to be as follows. So we want it to firstly apply plus and 0 to the leftmost subtree, and then it would go in the same way, and in order traversal would go. So it would what's after 1, it should go to 2, so it should say after 0, so 1, 0 plus 1, so this is the initial thing, and then it will go in the same way as the in order traversal, so it will go to 2, so then there will be a 2, and then it would go again to the 3. Okay, so the way we see here is that basically for what we did here in this little example is that basically folding the plus on the root node is means is exactly equivalent to applying the fold function to the left subtree, okay, and which is this thing, and then using that as an accumulator for the fold on the right subtree. So what that should look like is that. So that is the accumulator, and that is the fold on the right subtree. And the fold on the right subtree just happens to return +3 only. Okay. So and again, the fold on the left subtree is going to be equivalent to applying plus to the resulting of the folding function on the leftmost subtree, which is just going to be 1. So this is going to be the +1, and then use that as an accumulator to folding over the right subtree, which is 2. So, and then this is the accumulator for the fold over of the right subtree, which is 2. And then the result from that will be used as an accumulator for the fold here, as I said earlier. Okay. So the way we define that recursively, it should just follow what I was saying right now. So basically, firstly, I'll just get done with leaf case. So fold here L3 of a leaf and some data in the leaf and an initial accumulator that should return to us quite simply f and x and the accumulator. Okay. Yeah, it should take a function. Okay. So that that is the empty case, and then the second case, the leaf case, and then the second case we will follow exactly the pattern that I showed there. So a fold on a node, okay, should on a node with a left and an inner node with a left and a right subtree should be applying fold to the right subtree, but with the same function, of course, but with the accumulator that is with an initial accumulator that is the result of fold L3 on the left subtree with the initial accumulator S. Okay, so that is equivalent. So that is what I was trying. That is the definition of that pattern that I was showing you there. So let us try and see whether both functions are the same or no. So for example, I will do a fold. I will firstly try this function here on the tree that I'm writing, that's written there. Okay. So value of fold. So this is the example that I wrote in the paper there. So the function is plus, and the tree is that. So that is the tree, and the initial accumulator is 0. So here we have 6, and that should be the right thing, because here, there, you had 0 plus 1 plus 2 plus 3, which should be 6. Okay, so that is, we want to make sure that this function fold L3, that is a fold function defined recursively on the tree, returns the same thing. So I will say fold L3 on the tree. Sorry, this was not the tree. This is actually the in-order traversal of the tree. So here we're only talking about the tree. So in this case, it's also 6. So the fold, the function, the given tree, and the initial accumulator. Okay. So now, what we want to the next step is to prove that both functions are equivalent. Okay. And the way we do that, okay, so in general, when you write a recursive function, the way if it's a primitive recursive function, as in if the recursion follows exactly the constructors of a given data type, then you can just do perform the proof by induction on the argument on which the function recurses. So, for example, in our case, here fold L3 is a recursive function that recurses on the second argument, which is the tree, and the recursion follows exactly the patterns of this L3 data type. Accordingly, you can just do an induction on the second argument. Okay, and hopefully the proof will work. So let us try. So again, you should pause and try yourself. I will just continue. So what we have is fold F in order of any tree T and S as an accumulator is equal to fold L3 of a tree and S. Okay, so here is something wrong. Yeah, I forgot the function F. So let us try induction on the tree, and then go and see what happens. So it does not work, and why is that? So here, let us look carefully into the induction hypothesis and try and see why it doesn't apply. So here we have that. So the induction hypothesis for the left side and for the right hand side, okay? And we want to use it here on this conclusion there, okay? So we want to replace fold L3 of T1 and S. Yeah, sorry. No. So we want basically to get so that is the induction hypothesis, and that's what we want to rewrite. Okay, so fold F on in order traversal of T1. Okay, so sorry, that is the one. I'm sorry. Yeah, so in order of T2 here, we want to replace that. We want to use this induction hypothesis to rewrite that, you know, so that it somehow looks like that basically. Okay, but we cannot use the induction hypothesis here because simply the induction hypothesis is too specific. It has a clear constant S here. Okay, and in the conclusion where we want to do the rewriting, we have that initial accumulator, which is not S definitely. Okay, so what we want to do is to generalize the induction hypothesis to have this to be arbitrary S's. So then we can rewrite that thing into that, but then the S will be just replaced by that, and then that will match the right hand side of our goal. Okay, so in order for me to do that, I will do again a quantification over S and apply an O2, so that works. Okay, or we can do an arbitrary, but I will just say one more time why we need to do that. So here, the sub goal, the goal that we have, the left hand side of the goal that we have that we would like to write to match the right hand side is okay. So the hopefully would match the second induction hypothesis that refers to the right hand side, the right subtree. So we have a fold F in order T2, but the accumulator is different, so we cannot do that there. But we want to, and the reason that this cannot be matched is that this is the specific S that is in blue basically here. Okay, and here we have a different accumulator. So what we want to do is basically to generalize this statement to say for any S, and then in the induction hypothesis you will have also quantification over S basically. So we can do that by the quantification that I just did there, or we can do that by saying arbitrary S. Okay. Okay, so the same. Okay, and after we do that, generalization, what you have here is that this will be applied there, and then you will have this rewritten to the right hand side of that induction hypothesis, but with the appropriate substitution of S. So you will have fold L3F T2 and then fold L3F T1 of S instead of just this initial accumulator here, and that will happen to match exactly the right hand side. Okay, so that's how that proof should work. So let us try another thing to define a mirror function on that, on those trees that we have there. And the way, okay, so firstly, let me just slowly show you what a mirror function should be doing. So what a mirror function should be doing is, for example, in this example tree that's there, I want the function to return to me, like after mirroring. So I want it to return to me 3, and then you'll have here, this is that, this goes there, so it will be a 2, and that will go there, it will be a 1. Okay, So the way we would define that recursively, so let's watch what we did here manually. So like at every node I was reversing. Okay, so here for example I reversed the tree, the orientation of the tree and the left hand side, the left subtree and the right subtree. So we had here the 3 on the left instead of the right, and the 2 on the 1 on the right instead of the left. And then we did this recursively also. So we did here, what we did here is that I flipped the 2 and the 1. Okay, so you can also say that this happened on 2 stages basically. The first stage is that we flipped that root, and then afterwards we would flip the 1 and 2, so we would have here a 2 and a 1 like that. Okay, so what we want to do is to basically write a recursive definition that does what I just did now. Okay, so I recommend you pause it and then continue and try it yourself. Okay, but I'll do that. So function mirror so it takes a tree and returns a tree, and it should be primitive recursive, as in the recursion should follow exactly the patterns of the data type. So we have here of leaf. The leaf has a data content of x, and nothing should happen for a leaf. Okay, and for the other one, for the other case, we have a node and the left subtree and the right subtree, and what we would have is, what we should return is another tree that basically flips the left and the right hand side and then goes recursively and calls mirroring on all of their nodes, as I just did there on the paper. So node LR, so that would be node of mirror of R. Okay, so we flip this, and mirror L, so we can flip that. Okay, and let us try what that function will return to us when we apply it to our tree. So yeah, it did what we were expecting. So node 3, node, and so we had just like the top node. So it follows exactly the structure that was in the paper. So the top node has a left subtree that is a leaf node that has a content 3, and then the right subtree is an actual tree that has in it 2 nodes, 2 and 1 in that right order. Okay. So basically, like one way to check if your function does the mirroring correctly, or a sanity checking theorem for the mirroring function is the following. So you should be able to prove that the in-order traversal of a given tree is equal to the reverse of the in-order traversal of the mirror tree. Or let's just follow what's in the sheet. So the in-order traversal of the mirror is the same as the reverse of the in-order traversal of the given tree. Okay, so let's just try this lemma here. So in order that, three to 1, yeah, and here 1 to 3. So it's the reverse list, and again, as I said, because the function mirror here is again primitive recursive, as in it is written, it's defined recursively in a way that follows exactly the patterns of the data type, of the tree data type. So we can just prove it by induction on the variable on which it does the recursion, and in this case that is tree. So we just do induction, that is t, and it's going to induction on t, and then apply auto, and then done. Okay, so it overshot. So that's it for this. Okay, so our last exercise is about lists again, and so basically what we want to do is to be given two lists. We want to write a function that returns to you a list of lists, okay, and that list of lists should contain all possible shuffles of the given two lists, okay. And until now I haven't actually explained what do I mean by a shuffle. So what I mean by a shuffle is as it is written here. So a shuffle is a list that contains exactly so a shuffle of two lists, x's and y's, is a list that contains exactly the elements of x's and y's, but in the following way. Like any two members that come from x's should occur in the same order in the shuffle as those two members occurred originally in x's. So let me just demonstrate that with an example. One second. So, for example, if I'm given the list like 1, 2, and 3 and 4, so a shuffle of those two lists would be 1, 2, 3, 4. Okay, so this is a list that contains all members of the given two lists, and they occur in the same order in the original as they did in the original list. But for example, another example that is a shuffle is 1, 3, 2, 4, again because it has the members of the given two lists, and for any two elements that occurred in an original list, they occur in the shuffle in the same order that did occur in the original list. So for example, here we have 1 and 2, 1 occurring before 2 as it did here, and 3 occurring before 4 as it did there. Okay, but I cannot say that 3, 2, 4 and 1 is shuffle. That is not a shuffle, and that is because 2 occurs before 1, but on the original list only we had 1 occurring before 2. Okay, so what we want to do is to write a function. And let me just give you a basic hint. That function will be recursive. So we want to write a recursive function that, given two lists, returns to you a list of lists that is like what I just said. Okay. So let me just do that here again. So you should pause and try this yourself. But I will write it now. Okay, so all the list of shuffles. Okay. The alpha list and another list. Okay, and then gives you a list of lists. Okay. Okay, so in this case we cannot. I mean, like the most natural way to define this function is not to do recursion on just one argument. If you do that, then you will need another helper function that does the recursion on the other one. So the most natural way and the most elegant way to define this function is basically to do the recursion simultaneously on both arguments. And the way we can do that is as follows. So we firstly start with the case when the first argument is empty, or I'll just call x's, or let's say the other way around. The second one that is empty, y is empty. In this case, we should only return a singleton list, okay? X's. That is not a shuffle case. In the second case, we have the second argument is empty. Sorry, the first argument is empty, X's. In this case, we'll return all y's, okay? It should be easy. Okay, now the second case is when both lists are not empty. So the first one is an x and x's, and the second one is a y and a y's. Okay, and then that should be defined in terms of recursive calls. In terms of recursive calls on just x's and on just y's, okay? So let me just, before I go there, I will tell you that in Isabelle we have a function called map, okay? And that function takes, it's a higher order function. It takes a function, it basically, given a list of members of type alpha, and the function maps elements of type alpha to beta, it will give you the image of that list on the given function. So it will map every element of the given list into f of that element, where f is the where f is the first argument of map. So like that. For instance, so here we map every element. The function map will apply f to every element of x, and then it gives you the return the resulting list. Okay, so here we have shuffles. Okay, so we want to use the map here. So I suggest you again try and pause. I will continue, and so first time I will be appending x to the head of all the possible shuffles of just x's and y and y's. Okay, that is the first half, and then that should be appended to the other half, which is to basically map, just change the names to for readability, but it should be the same. So this is just the symmetric case. So here we're going to be shuffling all the x and the x's and just the y's there. Okay, so the function terminates. Let's write the readable way. So as you can see, the function terminates. That's what's said here, because with every call, one of the arguments decreases in size, basically. So either this one decreases or that one decreases. That's why it terminates. So so now what we want to prove is basically that any given shuffle, okay, any given shuffle z's, any given shuffle z's from the list of shuffles, okay, has the length that is the total of the initially given two lists. Okay, so I just would like to remind you that the function set here gives you the set of elements in a list, and this symbol there is just them demonstrates that Z is an element in that list. Okay. So this function, let me just say, because this function is not a primitive recursive function, as in its recursion doesn't exactly follow the patterns of any of the data type of lists or any other data type. It will have its own induction principle. So and what we should use is the induction principle that comes with this function, and that induction principle is induct. Okay, so here that induction principle, as you can see, follows exactly the structure of the function, and so we have a case for when the second argument is empty, and the case when the first argument is empty, and then the third case gives you an induction hypothesis for when the first argument has one less element, and the second and another induction hypothesis for when the second argument has one less element. And from those two induction hypotheses, you're supposed to prove that whatever predicate you want to prove on the two lists with the extra elements x and y. Okay. And in general, as you must have seen in the lecture, this follows these induction principles are always produced by the function package, and they follow the structure of the computation basically. So if you define a function recursively, you'll get an induction principle, and if that function terminates, if you define a function recursively and if that function terminates, you get an induction principle that that requires you to prove as many goals as there are cases for the defined function, and each of those goals will follow the structure of the recursion as I'm showing there. Okay, and in general, so let me just show you the general pattern of how that could look like of these induction principles. So if I have a function, a recursive function that is defined on case 1, for example, and that is a base case where we don't do any recursive functions. Okay, and then you have a function that is defined in a case 2, and then it has something, and then it calls the same function f recursively, but on case 2, on some argument that is smaller than case 2. And maybe it calls itself again on another argument that is also smaller than case 2. Okay, prime here. Okay, and the third case also that is recursive. Okay, this one, for example, calls itself recursively one time. Okay, and then etc. and n cases. So in this case, you will be given an induction principle where basically, if you want to prove a predicate for any, so this is just so case 1 here actually encodes a list of arguments. So case 1 here encodes a list of arguments. It should be like x1, x2, etc. And this is the same list of arguments, and this is the list of arguments. So if you want to prove the predicate for this list of arguments, for any list of arguments of that type that is taken as an argument by the function f, you need to prove as many sub-goals as there are cases. Okay, and those sub-goals will exactly follow the computation pattern. So this one is a base case, so you need to prove the predicate that you want to prove on just the base case. Okay, and here the second case is a recursive case, so it will give you a sub-goal that has an induction hypothesis, and from that induction hypothesis you're required to prove something, and that in particular, that induction hypothesis will be P of case 2 minus, and another induction hypothesis for the second case, case 2 minus prime. And from that, you're required to prove P of case 2. Okay. And again, here I'm writing case 2, but this is actually a list of arguments, and this case 2 minus is also a list of arguments, like what we have here, for example, in the Isabelle file. So, for example, when I say case 2, or that will be like if we look at this as one of those cases, so case 2 is just that whole thing, and case 2 minus is that whole thing. So it's just case 2. It's arguments derived from the arguments of case 2, but they are somehow less with some measure. Okay, in some measure they are less. Okay, and then here also case 2 minus prime, which is a second list of arguments that is also smaller from case 2, but that might be different from the case 1. Okay, and then you will get also another third sub-goal for corresponding to case 3, but I'm not going to write that. So that if you look into this general pattern here for shuffle and induct, you're also getting, okay, for the first base case, you like if you want to prove a predicate for a list of arguments that are equivalent to the list of arguments that the function shuffled takes, you must prove that predicate on the base case, which on the first base case and the second base case, and for the third recursive call, you will be given as many induction hypotheses as there are recursive calls, but on smaller arguments, and then you need to prove P on the bigger argument. Okay. So in any case, I'll show you how to use that induction principle to prove that this theorem about shuffling. Okay. So lemma says in set shuffles x's and y's, and then this means that the length of z's is equal to the length of x's plus the length of y's. Okay. So the way you prove things by induction within the computational induction principle, what you would do here is apply induction x's and y's. Okay. And we give the induction method, induction principle that we want to use. So here it's just shuffles that induct. Spelling problem. Okay. And let us start auto. So it didn't work. So let's see what's going on with the induction hypothesis. So here we have that case, for example, we have an induction hypothesis there. And okay, so here we want to we basically want to use that if we have two sub-goals. Okay, for the first one we want to use the first induction hypothesis to conclude that something about the length of A. Okay, so the first induction hypothesis, because the reason I'm saying we want to do that, because this matches that. Okay, but the problem is that this assumption now cannot be substituted for that one, so we cannot get that conclusion and use it to prove our goal. And the reason is, here we have this XA, and here we have the same specific XA. Okay, and as you might have guessed by now, what we need to do is to generalize this induction hypothesis so that it doesn't really talk about a specific XA. Okay, and let us just go back one step further. What is this XXA actually? This is just Z's. Okay, but in this case, Z's is a list is a non-empty list. So it has a head X and a tail XA. Okay, So what that means is that we need to generalize the induction hypothesis for any z's, not a specific one. So again, you can achieve that by doing arbitrary z's before you say the rule. Let's see what's going on now. Yeah, so the reason I did that again is because I just want to show you. I mean, you can even before the auto, if it's too complicated, you can also analyze it before then. So okay, so this one got discharged and this one got discharged, and we were stuck here, and that was divided into two sub goals. But let us look into why wouldn't we be able to prove something like that. Yeah, we have to go after the O2, because then the O2 does the case analysis and sees what happens if Z is empty and if Z is not empty. And if Z is not empty, then this is what you get. You have two cases. Z is either X and XA, or so Z basically comes from that shuffle, from the first recursive call, or Z comes from the second recursive call, which is that second sub goal. Okay. So that should be it for the tutorial. Thanks a lot for watching, and I hope you've enjoyed it. And please, if you have any comments, just say them on the Piazza forum. And just I wanted to note that this time I will not upload the theory files, and from now on I will not upload the theory files on the same day of the tutorial, because I actually want to give you some time to try and follow the video and build the theory file yourself. So thanks a lot, and talk to you next time.